Hi, and welcome back. So you would have seen in the last video where we actually calculated the reactions and we checked them using the sum of the verticals equals 0, that reaction A turned out that it was 34.67 kilonewtons and that reaction C was 61.33 kilonewtons. So we're now in a position where we can actually put those reactions in to our diagram here. So reaction A was 34.67 kilonewtons and reaction C was 61.33 kilonewtons. So now that we know our reactions, then we can move on to the next stage, which is to draw our shear force diagram. So first of all, I'm just going to drag over this wee ruler because the first step that we need to do is to drop down a few construction lines at critical points on the beam. So I'm just going to draw one down here at A, and I'm going to move that across to B, and I'm going to draw another one down here, across to C, and I'm going to draw another one down here, and across to here, another one slightly over down at D. Okay. You will notice that I have not redrawn the converted equivalent point load for the UDL, and that is because at the end of the day, when we go to draw the shear force diagram here, this is in fact a UDL and cannot be treated as the converted point load. So we do not drop down a line below that converted point load. Okay, so push on to draw our shear force diagram. I'm going to need a horizontal line, so I'm just going to pop it in there, and this line represents the actual zero shear line within the beam. So I'm going to put a 0 at each side, and I'm also going to label this. This is our shear force diagram. Okay, so we're now in a position where we can actually start to draw the shear force diagram, and we're going to work from left to right on the beam, taking into consideration points A towards points B, C, and then on to D. We're going to start off at 0 here, and at A we have an upward reaction of 34.67 kilonewtons, and therefore, at least in proportion if not to scale, we go up as far as getting our 34.67 kilonewton point, always writing in the values, and then I join, well, as best I can, those 2 points together. As we move then from A to B, you'll notice that we have a 4 meter length of this UDL to contend with, and it is 12 kilonewtons per meter times the 4 meters, which is going to give us a drop of 48 kilonewtons. So if we're up 34.67 kilonewtons here, and as we travel across to this line down from B, we're going to drop by 48, well then that is going to bring us down to a point 13.33 kilonewtons below the line. And I'm just going to pick up a line and draw that in there. So we're now 13.33 kilonewtons below the line at point B. At point B we've also got a vertical downward 10 kilonewton point load. So if we're 13.33 below the zero line and we're being pushed down a further 10, then that is going to bring us down to 23.33 kilonewtons below the line. And again, we join that up down to there. Okay, so we've now finished with point B, and we're going to move from left to right again from B towards point C. And here we have another portion of the UDL, 2 meters in length and 12 kilonewtons per meter on each 1 meter length. So therefore 2 times 12 is 24 kilonewtons of downward force between B across to C. So if we're 23.33 kilonewtons down at this point and we're being pushed down a further 24, well then we're going to be down to 47.33 kilonewtons by the time we get to this point. And again, we have to draw a line between those 2 points. We've now reached point C, and at point C you will notice that we had the reaction C, which was an upward reaction of 61.33 kilonewtons. So if we're down 47.33 and we're being driven back up by this reaction by 61.33 kilonewtons, then you will find that we will be pushed up to a point 14 kilonewtons above the zero line. And again, we need to connect those 2 lines together. Finally, we push from point C across to point D, and as you can see across the beam here between C and D, there are no loadings, and therefore our shear force diagram will continue across horizontally unaffected because there are no loads to do anything to our shear force diagram at that point. When we actually reach point D, you'll notice that we have a 14 kilonewton downward force at this point, and we are up 14 kilonewtons on our shear force diagram. So obviously if we're up 14 and being driven down 14, it will bring us back to 0. If it doesn't bring you back to 0, or at least effectively pretty close, something like say 0.02 or something because of maybe rounding up or rounding down on your reactions, then you have a difficulty or a problem in terms of some of the calculations that may have been carried out as you actually moved across the shear force diagram. So obviously you need to take a look at that. Everything above the zero line is considered positive shear, and everything below is considered negative shear. One of the main points in actually drawing the shear force diagram is to actually find the maximum shear force value. And for this, even though this is negative shear force, this is still the larger number on the diagram, and therefore is our maximum shear force. And that is what we have to list down. Maximum shear force equals 47.33 kilonewtons. Okay, now there's just one last point that I want to actually make before we finish up with our shear force diagram, and that is here, which I'm highlighting with a sort of like a blue dot here, and here are 2 points of zero shear as we move across that shear force diagram. And the scenario with those two is that points of zero shear, I'm just writing this up for you, okay, points of zero shear may indicate points maximum bending. Now, the purpose of us actually drawing the shear force and bending moment diagrams is to calculate these maximum values. So we've found the maximum shear force value here, and when we go on now to calculate the bending moments and draw our bending moment diagram, it is in essence to find the maximum bending moment. So really, whenever our shear force diagram is indicating to us that there is a possibility that this may hold our maximum bending point, then this becomes another critical point for us. And because of that, then we need to drop another construction line down through here. Oops. Okay, and that is obviously because we do need to calculate the bending moment at this point right there. Okay, and I'm just going to reference that. Oh, sorry. Change this guy. I'm going to reference that as point A1 because it's sitting between A and B, and I want to calculate the bending moments for that as we go along, and that will be at point A1. So the next time we come back on the following video, then we will be calculating the bending moments and drawing the bending moment diagram. So really and truly what I would like you to do at this particular point in time is that if you jump past video 3 at this particular point and go and take a look at the practice exercises that I've put up there for you, if you can try and take one of those practice exercises, those beam scenarios that I've given for you there, and calculate the reactions and draw your shear force diagram, find your maximum shear force and see if there are any points of zero shear which may indicate points of maximum bending for you. And once you have that done, then return and watch video 3 and take a chance then at calculating your bending moments and finally drawing your bending moment diagram, and hopefully maybe see if there are any points of contraflexure on the beam. Okay, so until that, then I'll chat to you on video 3. Thank you.